Okay, in this chapter, we look at the delay routines. How do we write delay routines? And we look at where do we write in a program and also where the applications are. So we look at delay routines. So the first part is the delay loops. In many applications, it may be necessary to implement a fixed delay in an assembly language program. And what we normally do is we write a short delay loop, and then we can loop that again and again to get a longer delay. So I'll explain to you how we implement this. So if we look at a pick instruction, and it's executed in one instruction cycle, and we have already looked at it earlier that one instruction cycle means is the 4 divided by the clock frequency, so it is about 1 microsecond. So we've looked at that before. And in a branch instruction, you have already come across branch instruction, and you will find if branch takes place, then it takes 2 instruction cycles rather than 1 instruction cycle. So again, we will have a look in detail. Time delays are generated using delay loops. And how do you do a delay loops? How do you create? What we normally do, we select a memory location and set a value into the memory location and use the memory location as a counter. And then that counter is loaded with a number. And then we decrement the number. So the number is decremented again and again until the counter value goes to 0. And that itself is a delay. And time delay loop is normally written as a subroutine. So in a main program, if you want a delay, you call a subroutine, and the subroutine itself is subroutine is the delay, and when you finish the delay, come back to the main program. Now, when you are writing a delay loop, we have to make sure that exact timing, exact delay, exact duration is required. Then we need to start to calculate every instruction takes how many clock cycles. That's very important for us to know. So I'm now going to start with one delay routine and a simple example and look at a small program. So in this example, a delay loop, a TL millisecond, we need to achieve a delay in millisecond, not in microsecond. So what we are saying, we set up a counter 1, as a memory location, H20. So memory location, hexadecimal 20, we put a value here. The maximum value you can have is FFF, 255 is the maximum value you can have. And we set that as a counter, and we load a value there. So first part, this is your subroutine, delay routine. Move W register with the value 255, decimal 255, or hexadecimal FF. Okay, this is equal to hexadecimal FF. And then move this value, the W content register, to the counter. The counter is here. Now counter is now loaded with FF, or 255. So that's your first part. And the second part is, because I need exactly roughly millisecond, I introduce few instructions. In this case, NOP instruction. NOP instruction is no operation. That means you can look at the assembly language programming manual. No instruction, which takes 1 cycle. Sometimes you need to insert this one to get the exact timing. And I have put another instruction as well here. You can have as many you want, but you don't want to have not in a program many. But I just want to show you a few examples here. So that's why I put 2 no operation instruction. It does not do anything. It just wastes the cycle. So it also takes 1 instruction cycle. Then I'm saying decrement the counter. So the counter is this one. It's decremented by 1. So we decrement by 1, and then put the value back into the location 20. This 1 stands for, you put the value, after you decrement it, the value goes back to the same memory location. That's what this 1 for. If this was 0, you know, where does it go? It goes to the W register. But in this case, we want to retain this as a counter. So we want to make sure that that has 1, so that which we have done. Okay, we now look at the next part. So how do we get the so the value now after the decrement, it was 255E loaded with, decremented once, 254 is the value there. And then we are saying that in this instruction, when it's decrement, when it goes to 0, that stands for 0, it will jump to the next instruction, that is here. If it is not 0, it will go back to this. And it will keep doing this one until the counter is 0. So go to delay millisecond is 2 instruction cycle. When it does not branch, it is 1 instruction cycle. When it's branching, when it comes from there to here, it will be 2 instruction cycle. Every time it branches, it's 2 instruction cycle. Here also I introduce an up instruction. You don't need that one, but I just wanted to get extra, just to show you how to count and how to introduce extra delay. And then you return. Return is also 2 instruction cycle. So it's a subroutine. So in this case, this is a subroutine executing this one until we started with 255 decimal, and it just keep going 254, 253. Eventually, we have got to 0. When it comes to 0, it jumps from here to that, and then it executes this, and then it goes back to the main program. Let's now calculate how long does it take to do this. So here is the calculation. Now this shows you when the counter is 0, it goes to go 2. So when it's 0, this is skipped and it comes here. That's what is written here. Now let's look at delay routine. Okay, so in the delay routine, that and that is 2 instructions. So 1, 2 instruction cycle. How many times is going to be in this loop? You will find this will, because we fed with the 255, this loop will happen 254 times. So 254 times, and then the next time it will come out of it, right? So you will find here that this instruction, so these two then would have 1, 1, so that's 1, 1. This instruction is also 1 because it's not jumping. Then this instruction going back is 2. That's the total number of instructions. How many times it will be executing that one is D1 minus 1. Whatever value you put in there, minus 1. In this case, 255 we put in there, 255 minus 1 times. And then when it comes out, when it jumps from here, that is 2 cycles. So it must have 2 cycles there. And then return is 2 cycle. Plus, you must remember, plus, this is 1, so that one is there. Plus these 2. Because you had there was 1 there in the counter, then it goes that cycle, when it decrements it becomes 0, so it just jumps from here. So these 2 need to be included in the delay. So that's what these 2 are. And then when you subtract and add them, simplify them, this will be your total number of cycles. One cycle, instruction cycle is 1 microsecond, so that's your total time. If you calculate that, for a delay of 255, you will have 1.279 millisecond. For delay of 200 provides 1.004 millisecond, this particular instruction. You can rewrite this one without also you can rewrite them without these instructions. You can rewrite this one without those as well if you want. But I just inserted them to show you. But remember, when you have 255 here, it will go through 254 times in the loop, and the 255th time it will execute that, and then it jumps from here and then that. Remember that. That's why you got 1, 1, and that one will be 2, and that is 1, and that is 2. So that you will have at the end. That's 1, 1, 1, jump is 2, and return is 2. That's what these ones are. And these ones are, you are doing 254 times that, and these two belongs to these two. Okay? So hope you have understood how to introduce the delay. Let's move on to the next part. This one is a group exercise. I would like to see all the students together, a group of 2 or 3 together, sit down and work out this. There are 3 questions I have given. It's 1, 2, 3. I've given answers for 2, that one, and that one. So if you start with the first one and see whether you get that answer, then try to do the second one and third one I've given. If you got this right, you will get the right third one correctly and you can check the answer. If the answer is not correct, if you didn't get this right, that means there's some error you have made there, because the same principle is applied here. Okay, in this case you will see that takes 1 cycle when it executes it, and that takes 2 cycles, so that's together is 3 cycles. How many times it will do is depends on counter minus 1. Counter minus 1 is k minus 1 times 3, plus at the last one when it sees it's 0, it jumps out, which is 2 cycles. That's what that 2 comes into play. Anyway, you can do the calculation. Similar principle here and similar principle, and see whether you are able to work out all of these. Once you have got this part correct, then you will able to start to do some activities where you can actually connect LEDs, and flashing an LED at a particular rate, you can do that. Now we look at nested delay loops. So if you want, when you look at the earlier one, we only had in terms of millisecond. Now if you wanted to go more than a millisecond, you want to go in terms of second, then you use nested delay loops. So the delay program shown in the previous slide it provided you with a short delay. There are many occasions where we need a longer delay. So one way of obtaining this is by using nested delay loop, where a second delay subroutine calls the first delay routine. So you've got a first delay routine. So here's the delay routine here. And here is another one calling this one many times. So by doing that, you can actually increase your delay. So let's look at one example and see how we are achieving this. So I'm setting a counter with 21. Previously I have the counter at 20, and I've already implemented a delay for that, which gives me roughly 1.3 milliseconds. So what I'm doing, a second subroutine starts here. Second subroutine is going to call the first subroutine that we wrote in the previous slide. So move literally 100. So I'm going to call the previous subroutine 100 times and move that into a counter. Counter is H21. Now, what I'm doing is I'm calling my previous delay millisecond, previous slide, I implemented that, which is roughly 100, 1.00 millisecond. And then now I'm decrementing the counter, this counter, and I'm looping this, calling and looping. So every time I go through this, I will go whatever value I put in, which is 100, so 99 times I'll be calling that. No, 100 times I'll be calling that, right? And then when it's 0 counter, you jump to return. So you really need to work out this. How does it, what value you get? You see? So first 2 lines is 2 cycles. And going through this many times is, we know k minus 1 times This instruction we have already worked out as 1004. And 1004 is the delay. And then decrement the counter is 1. Go to is 2. Calling this subroutine is also 2. So that's your total delay in that part. Plus one more. One more is what? The last cycle is executed that one, and then it branches out and then comes here. So that one is 1004, and this branches out to this one, that is 2, and then return is another 2. Plus, this has to go there to really call that one. So that will have 2 as well. So anyway, you can try it out and you will get, that's your total number of millisecond. That's about 0.1 second delay. So the principle here is basically, all we are saying is that you have a smaller delay and call them again and again, you get a longer delay. That's the principle behind it. And it's important that when you are doing this calculation, you're going to make sure you have understood very clearly, because if you haven't understood this one, later on, if you give a small code and ask you to calculate, you may not be able to get the right number of cycles. So it's very, very important. If you're not sure, make sure that you ask myself or the tutor later on. A longer delay can be obtained by using a loop within a loop principle with a single subroutine. You could have multiple subroutines. You could have another subroutine here. So you could get longer delay. So it's basically delays wasting instruction somewhere in the subroutine and then come back to the main program. So this is your main program. This is your call routine for delay. So this has got delay, and the delay is many delays loop, and then you come back here. So if you want, this delay is what you work out, how many milliseconds, how many seconds that you want. And if you want microsecond delay, you stay in the main program, because one instruction cycle is 1 microsecond. So this is another group exercise. I would like you to try it out and determine the number of instruction cycles taken for the delay routine below. So it's a very long delay, and once you've got together as a group, then check among yourself, discuss among yourself, and see whether everybody gets the same answer, and then you can check that with your tutor. So it's very important. This delay has got 3 counters: counter 1, counter 2, counter 3. So you should, you're getting longer delay than what you had before. So you should try this one, everybody, before you move on to the next section. If you are not sure and if you didn't get the answer, please make sure you get the answer before you go to the next slide. So we know how to create delays now. Now we will do a few examples. In this example, I want an LED chaser. What does that mean? It starts with one LED is lit, and then it moves to the next one. The one is turned off, the next one, and the next one, and the next one. It comes in a sequence. So just one particular LED lights, and all the way through it switches to the next one, and the next one, and the next one. It's come in a loop. So that's the what that we're going to do in this. Here are the 8 LEDs connected to port A. So 8 LEDs are connected to port A as shown in the diagram, and your program has to turn on and off one LED after another. Moving from left to right, we want to move from left to right. You can move from right to left as well, but in this example, left to right. Basically, this is on, then this is off, and that's on, then that's off, and that's on. First, everything is on first, and this, and repeat the sequence using a delay loop of 250 milliseconds in your program. 250 milliseconds, like 0.2 seconds. So you will be able to see the sequence moving pretty well. If you make this delay very small, you will find all the LEDs will be lit at the same time. It will look like everything, even though they are moving fast one after another, it's so fast you won't be able to see. Okay? So let's look at this program. How are we going to do? Naturally, this one's initialization, that you know how to do it. This is your main program. We first select bank select Ansel. Ansel is in bank 3 is automatically selected, and we clear W register and then move them back to Ansel. You have done enough of those, you know that's the digital input output. Then we move to the Ansel H because we are interested in port A. So you can, instead of doing this, you can do other way around as well. You know, you can say here, this instruction can be written differently. If anybody can tell me, it will be, you can say, this will be bank cell. You can do that. It automatically, assembler does know that. If this is not available, then you're going to do this way in assembler. Okay. And what you are doing is you are clearing the push A as register and set port A as all output, because clearing means all zeros. That means port A is going to be all output. Now we want to then select port A. Port A is in bank 0. So port A is in bank 0. You can select if you want to do, before you do instead of that instruction, you can say bank cell port A. You can do that as well. And then once you have selected port A, you clear port A. So the output is all zeros. So this is 0, 0, 0, 0, 0, 0. None of the LED is going to glow now. So that's the first state. All LEDs are turned off. So once we have got this, so we have initialized everything and all the LEDs are turned off. Now we are going to start to do this. So we go to the next page. So what do we need to do here? We start with, we want to make sure that we have to have, we move 80 in the register. So we want to make sure that's 1. So that's the first part. And move that value to the port A. So LED connected to most significant bit will be on. Because the sequence, this has to move here, this has to move here, this has to move here, and so on. When it comes, it has to move through the carry. That's the way the instruction works. So every time this moves, this carry gets in. So it's important that carry bit is 0. We are going to make sure carry is selected 0. That means we're going to make sure that bit is 0 before we do anything. So what we have done is that we have cleared the carry. In the status register, in the 0th bit is the carry bit. So we've cleared that. So definitely carry is 0 now. Okay? So you've understood that part. So once you've understood, now we can go to the next instruction, see what we can do with the next instruction. So we cleared the carry. We know this is on now. And what we need to do, we need to create a delay of 250 milliseconds. So you should write a delay routine separately as a subroutine, which is 250 milliseconds, based on our previous knowledge in the previous slides. Once it executes subroutine, and it will return to this line. This line says you are going to rotate right contents of port A through the carry. So this is your contents of port A, and you can move that direction. So the 8th bit, so the last bit one will move there, and the carry bit will move there. So it's just the rotate instruction is what you're going to use now. So when you use the rotate instruction, earlier this was lit, and this now moves here, then this will be lit. The carry is 0, carry will move across, so this will be turned off. And this is lit. And that instruction does that. And it just rotate and put it back in port A. Now we want to test whether we have reached up to that point. Okay? So we are saying we want to see whether, test if you have reached PA0. That's what we are looking at the bit 0 of port A. We are looking at that with 0. And if we have reached that, then what we need to do, we just go back to the start. So if you have reached it, you go here. If you haven't reached it, we need to keep shifting it. And that means you go back and go to that part and keep looping. And that's your program. So in summary, the LED is you set up the initialization, and then after your initialization, you put a value here, 1, and you put a carry 0. Then you use rotate instruction to rotate that one. These were all zeros earlier because we initialized the ports, right? Now this one moves here, and this one moves here, and this one goes here, this one goes here, this one goes here, and so on. That's the rotate instruction. And then this one moves, that one, this one, little by little moving every 20 milliseconds, and when it reaches done, it then comes back. Now the question is, you may ask, do we need to test this? Can't we just keep moving all the time? Yeah, you can do that. So when I give a program, because I want to introduce a lot of instruction, I do it in a kind of a non-optimal way. So that you will start to think, every program I write, you have to sit down and think, is this the easiest way to do it? Is there another way of doing it? You should try the other way, right? There will be other ways of doing it as well, right? So that you then get a better knowledge of, you will feel that you have done it yourself. No? Okay, we now move on to the next part. Eliminating switch bounds. You know, when you have switches, so like for example, let's say a switch those days, if you look at, I mean, the switches nowadays are pretty good, and they don't have less bounces. This is a movable platform. When you press that, that thing touches here, and then when you release it, then that part is disconnected, you know. So switches are like, you know, like that. There's got a plate in there, and it kind of touches this way and then disconnect them. Every time when it touches, it makes a contact and then not make a contact and make a contact, not make and break for about 5 milliseconds before it actually. So when the switch is in an open position, so I can say that it's in that position now. It's an open position switches. It's like a plate, and that's where the base is. And when I press this one, it'll make a connection first. It'll make a connection, then it automatically disconnect, and then make connection, disconnect, and then eventually settle. So there is a transition period of 10 milliseconds. The switch bounces. So we need to have some sort of a debouncing technique. So we will write it in software. So you see, mechanical switches have a bouncing property when the switch makes contacts and it opens and closes. And switch contacts normally bounce for about 10 to 15 milliseconds before staying together. So this is about 10 to 15 milliseconds before staying together, I mean before it comes to close position. And this is also true when the switch opens. When you open the switch, the same thing. After you have pressed it, so you had a switch like that, and that is, you pressed it, and when you take it out, also it goes, bounces, and then come to open position. So we need to make sure that these are not counted as various counting, you know, multiple counts. We only need press the switch, we have got one pulse. When you release, we are going to see it as 1. So we must have this amount of delay in your program, so that when you detect, when you go from high to low, when you detect that, you delay for so many time, 10 milliseconds, then read it again, are you still low? Yes, after 10 milliseconds low means, yes, the switch is closed. Then you open the switch, you detect a 1, so you detect a 1, then you stay in a delay of 10 milliseconds, you then check it again, and if it's yes, it's a 1, that means it's open. If it's not a 1, then it's not open. Okay, so you need to really implement this. So the microcontroller may register many of these bounces as instead of one push, it will see it as many pushes. So there are software solutions. So the first detection of a change in a switch, how do you do it? We detect them, then we give them a delay of 10 to 15 milliseconds, and then check the switch again. And if it's still pressed, then it's correct. And then you move on and assume that's already pressed, the switch is being pressed. You can have a hardware solution. Instead of a software solution, you have a D-type, the Schmitt trigger, and you look at the Schmitt trigger output, and this resistor capacitor provides the delay that you need as well. So you can do a hardware solution, and you can draw this circuit, debound circuit, this circuit, Schmitt trigger circuit, using latches, and see whether you understand this part. It's important that you must have learned this one in your digital circuit course. If not, look up an example, or ask me in the class, or ask the tutors in the labs. Okay. So we're going to do an example. So switch debouncing using a delay loop. And this example you have come across earlier. Earlier we only used small fixed switches. We didn't look at push button switch. We kind of used as a slide switch last time. Slide switches won't cause that bouncing problem. So this is a push button switch. Like in any instrument, you've got a push button and push to close and release to open. That sort of a button. So you can get this one from the stores, that particular button, to test this particular example. So what we want to know is that we connect this one to PA7, and if it is pressed, we glow an LED. Right? If it's open, we turn off the LED. And as soon as you press this one, as I said to you, it's already 1, and when you press it, it'll go up and down and then go low, because this is low. And then when you release it, it'll go up first and then bounces and then go high. That's high, and that's low. That's the way the switch will behave, as I explained to you before. So how do we do this one in our programming? Leaving out all of these, do you know how to do this one? We select the bang 3 and ansel 3 and clear them. That means everything is a digital port. Then we select the touche bang, which is bang 1, and we set this binary pattern into W register. The reason is the binary pattern is that this one is also input. So 1 1 and 0 0 1 1 0 0. That's the pattern. We need to put it in Trish. So we have done Trish A actually. So we have done that one. So this is an error there. That's Trish A, yeah, not B. And then now we go and select port A, because we have set up port A now already. Now put the value into port A. That's what we want to do. Okay, we go to the next part. So you know these all selections are here. I always now put these back to you so that you can see when you say bang cell and cell, what it selects this one. And when you say touche, it selects this one. And when you say port A, then it selects that one. The bang cell command does all of those. Now, how do we do this question? Okay, let's have a look at it. So main program, what we want to do is we want to make sure that we clear PA5. PA5 is this position. We want to put a 0 there so that this is off. This LED is off initially. Because the switch is not closed, or normally it's open. Therefore, that should be off. So what we did is we clear port A bit 5. We have cleared that. Now we want to test this bit. Has the switch been closed? So what we do is we go and see, is this bit is 0? That's what we are saying. Is this bit is 0? That means if the key is pressed, it is 0. If it is 0, branch to call. If it is not 0, then you're saying keep looping and check the key all the time. It's like a polling. If it is 0, you call routine, so you are 1 and it detected a 0 and it will bounce before it comes. So you call a routine of delay 15 milliseconds. You know how to write the program for 15 milliseconds. Once you have done that, then you check it again. Is it still 0? You detected 0, 15 millisecond delay, you check it again. So you are checking again, if the bit has been set again, it's not set, therefore now you move on to the next one. It's not set, so then the next instruction, you have to turn on the light, because you have detected it is. You turn on the light. And then you come here, the next part of it. So you turn on the light. Now you keep checking the status of this one, because you may now release the button. So you are now again checking, is the bit set? If the bit is set, that means you have released it, you know. If the bit is not set, you keep, because it was pressed here, this part is pressing, this part is releasing. And if it was, you detected that it was released, that means it was 1. This one, if you release this one, this become 1. That means you jump to call routine and call for 15 milliseconds. When you come out of the 15 millisecond, so you detected from low to high, and it will go up, down, and eventually it will go there, right? So you're going to check whether it's again 1. Yes, if it's 1. If it is 1, then you go further down. If it is 1, you clear your port bit, because it's 1 means not pressed. Turn off that, and then you go to wait key P. So wait key P is here. You start again the whole lot. Now you may decide you want to write it differently. What could you do differently? You may say that, okay, I'm not going to test this bit for clear, I can test it before set. You can do that. You can do differently. If you do clear test, if you are branching based on clear, you can branch also based on 1 as well. Then you have to adjust the program accordingly. Okay? So every time, and as I said to you, when I write a program, you also need to look at, can we write it differently as well? That's how you learn. Now, using all the knowledge that we had, we now look at keyboard scanning, which is very important. That you will normally have keyboards of 9 keys, 16 keys, 4 keys in various applications. Their keyboards are set up in a format of a row and columns. That's the way keyboards are set up. So when they're set up rows and columns, you could have only 4 keys, you could have only 9 keys, or you could have 16 keys. So whichever the way it is, in this example, 16 keys, we need to know which key is pressed. That's the part we're going to learn. And how do you write the program to detect, when you have so many keys, to detect which key is pressed, and then what action you take. Okay? A keyboard allows numeric and alphanumeric information to be entered, and is widely used in photocopiers, central heating controllers, washing machine, everywhere. The keyboard consists of a touch-activated switches. They are arranged in the form of a matrix, and that means they are columns and rows. Most of them are arranged in there. They are not in one line. They will have columns and rows, and the way I have got it there. When a key is pressed, it connects its row to a column. That's what it does. So basically, if I press this key, here's a key I pressed, that key is pressed, mean it connects me that row to that column. And that's the principle we use to detect. And we use a row scanning technique to identify which key is pressed. We want to know, we use a technique called row scanning. We'll come back to that in a minute. And we send a walking 0 through it, and then detecting the 0 through a column. Okay. So what we have done is, because we have got altogether 16 keys here, they are arranged in a row versus column. I've connected PA7, PA6, PA5, PA4. That means 4 lines as rows here. Row 1, row 2, row 3, row 4. And then I have got columns, and the switches are such that that's connected back to PA3, and that's all are connected back to PA2, that all of them are connected to PA1, and the last column is connected to PA0. So that's how we have all the switches set up now. And so you will find in port A, 4 of the lines are output, 4 are input. You may ask me, do we have to do all in one port? No, you can have 4 lines coming from port A and port 3 reading the remaining 4 lines. That's fine. But in this case, I have it this way. So the question is now, what do we do? How do we detect this key press is the question now. So how do we do that? So what we do, what we call is a walking 0 pattern. So I send a 0 here, all the other ones are 1. That's all I do. And I read the keypad in here. When I read keypad in, if all of them are 1, what does that mean? No key is pressed. In this case, this is 0. Therefore, that should change to 0. And then I move this 0 to here, and you will find that is 0. So that means this particular row is energized. Earlier that row was energized. Now this particular row was energized. And read the pattern. When I read the pattern, still that key is pressed. So that means this is 1, that is 1, therefore sorry, I made a mistake. Let me just go back here. Just go back here. A small, tiny error. Okay. So when you send a 0 here, you will find this key is the one on which is pressed. So that row is not energized. That's 1. Therefore, all these are, if any of these keys are pressed, then there will be zeros. But none of them. This is only pressed. So the output that you're going to read, what is coming in is all 1. So we haven't detected it. I'm trying to detect that key. I want to detect that key. What do I do? So next pattern I say is I'm sending this one. That 0 goes here. That's a walking 0. So now that's 1, that's 0. And I read the pattern. Still all are 1 because this row is energized and this key is here. So I get all 1. Then I know it's not second row. Now I go to third one. When I do the third one, I've energized that one, and when I read it, I know this is connected to this 0, so that 0 gets in here. Now I've read this pattern. From the pattern, I can figure out which key it is, because I knew which row I energized it. I know which row I energized it. And from that, I can work it out which key is. Now walking 0 goes to the next one. When it goes to the next one, this key is there. So these are all, this is energized, none of these are pressed, therefore it's all 1. So only one case is going to be 0, and I know which row I energized, I know which bit is 0, from that I can figure out it's going to be my key number, this number, key 9 being pressed. Whatever number it is, it's not key 9, it's called key 5. 1, sorry, this one. So it is 9, key 9 is correct, not 5, key 9 is 5. And that's how you detect, and we'll write a program to see this one, okay? This is a very important exercise that you need to do. You need to start to figure out the algorithm first in your mind before you write it. So here's the program. So what we need to do, I made this as a question where that you scan the 4x4 matrix keyboard. You will be told if it's a keyboard, is it a matrix form, you will know you can energize something rows and read it from column. If somebody turns around and tells me, can I energize the column and read from row? Yeah, you can do that. But you need to adjust the port accordingly, read and write. Okay? And connect it to port A, and when a key is pressed, whatever the value of the key should be displayed on these LEDs, not hexadecimal display, just the value. So if the value was 2, that will be 1, all others are zeros. If the value was 16, then this will be 1, all the others are zeros. So that's how you need to display this particular question. Okay, we will look at this question, how we do this one. So we want to have 2 memory location as a storage, where we can temporarily store information there. And these are all, as we did before, is selecting digital ports. And once you have done that, select Trichet and put all zeros here, all ones there, because they are input. And then you move the value Trichet, and then you clear Trichet because you're going to keep this as an output. And then you select bank cell port C, and then clear all the values, so these all will be turned off initially. So that's all the first part of initialization of your keys. Now let's look at it, what we need to do. How do we do this program? So let me just move this upwards. Okay. So keyboard scanning is the program, what we call it. First, I want to make sure that I will be using rotate instruction somewhere. So I need to make sure that I clear, I want a carry bit to be set to 1 or 0, whichever it is. In this case, I am going status register, that's that one. That carry bit is going to be set to 1. I've set that to 1 at the moment. We'll come back to that later on. Now the question is that I want to energize that row now. Or here, this one, I want to energize. So I put in a pattern, and this pattern such that PA7 is 0. So this is 0, all the others are 1s. I mean, these you can't change, they are input, these ones are input, so only the output can be changed. And then what I do is I take that pattern, whatever that pattern I had, that pattern will be stored in the store. Store location is H20. So the H2 and T would have this value, my 0, 1, 1, 1, then all 1, 1, 1, 1. That's my H20. I have 4 times I've got to energize. 1, 2, 3, 4. Therefore, I need a counter to make sure I have energized 4 times. So I have a counter here. A value 4 is going to go into the counter, which is H21. So it's going to have a value 4, that's 2, that's 1, 0, 0, 0, 0, 0, 0, 0. That's H21, that's H20. Those are the values I have in the counter. And I've stored them as well. This means you're storing them back. So I'm now moving into the W register the content of that row pattern. And I'm sending that to the port. So I have energized this now. This is happening now. I've sent it to the port. Now I am reading from the port into the W register. So that's the instruction, move F. So port A is moved into F register. So into W register. And then I have got a NOP instruction. And you may ask me, why do you have that NOP instruction? The problem is that as soon as you send the 0 here, and if you are keeping pressing, and it has to then read this one. And there may be, immediately you are reading it. You see, you're sending it and reading it. So what I would like to do is a small delta. You send it, and then you're going to read it. So I just want to have a NOP instruction, contents to appear on the pins. But you will find, you can just Still will work. Okay. Now I have the content in the W register, and I want to do an exclusive OR with the store content. My store content is in here. If I do an exclusive OR, what do you think you'll get? If none of the keys are pressed, this all will be 1, 1, 1, 1, 1. These are already 1, 1, 1, 1, and that's 0. That's 0. So if you do an exclusive OR, everything will be 0. If the result is 0, you say no key pressed. We haven't pressed any key. That's what it says. So no key pressed. If key pressed, find the key. So if you do find if the key is pressed, so this is if it is, so what happens is then, if it's not pressed, it jumps to this instruction. And then what you do, you rotate, you store the, you take the content, rotate in one direction. So you are going to rotate this way. So when you rotate, the carry was set to 1, therefore this will become 1, and that becomes 0, and so on and so on. And then you decrement the counter. You're saying you've done the first rotate, now you can decrement the counter because you can only do 4 times. And you check the counter. If the counter is 0, then you've got to go back and start again. That is key scan. If the counter is not 0, you then go back and energize again. And the next port, you send it again, and that's how you do read the value. And you must have this particular value stored. Okay? One thing is, in this example, if no key is pressed at the time, that's where you're testing it, you go to the next, energizing the next row, and then you keep executing the next instruction. If key is pressed, when we know that key is, when the status bit is, when you check the key is pressed, then what you do is you call a routine, which is called LED display. So in the LED display, which we haven't written here, where it's a subroutine, where it takes the data, the data of the value that you have read in here, and it takes this pin value, it checks this value, and do a combination calculation and convert them into a code and send it to this display. And that part I haven't written here, which I would expect you to try it out. If you are trying this experiment, you should write this display code routine yourself to say you read the content at that point when the key is pressed, when you detect the key pressed, you need to know the content of all of these. What you said, what you read, you then form the value, which key is pressed, you just translate that into a value, which is anything between 1 and 16, and then the binary pattern is sent to the port. And that will be done by the LED display. So you must write the LED display subroutine for this program to work. Okay? So that's alone is a kind of a longer program. When I say long, I mean another 7, 8 lines. Once you detect the key pressed, so this is mainly energizing the row and keep going in loop until you detect the key. Once you detect the key, you get out of the main program, and then you call a display, and that's where you actually find the code and then send it to the port or port C. Okay, so that's that part now so far. I think we've got enough examples for you to try out so that you have an idea of exactly how do you introduce a delay in a program of various duration for various application, plus how do you read a key. If a keypad is given in a matrix form, you energize row, read the columns, and then you figure out which key is pressed. Okay, so that's something that you can try it out. Now we move on to another section on this part in this particular chapter, which is the indirect addressing. Very useful that you need to understand this particular indirect addressing. What is indirect addressing? What is direct addressing? There are two aspects: direct addressing, indirect addressing. Direct addressing means in the program you give the address and the computer knows it just have to go to that address. Indirect addressing means it does not know where to go. It will go and find the address from somewhere else and then go to that place. So what happens is that if you want to explain that so I want to go to this particular person. I know the address, so I can go directly to that person. But I didn't know the address of this person, but I go to somewhere else, that person knows the address of this, and then I come here. That's called the indirect addressing. That's called the direct addressing. Okay? So you need to understand both. Direct addressing means you need to have that information. Indirect means you have to go somewhere else to fetch that information and then go to that particular location. How do we do that? How do you do it in this particular microcontroller? And that's the next part, and which is also very easy when you understand. We are now introducing additional information for you, additional instruction. So indirect addressing is useful when you're creating a list of data to be stored in a data memory. You want to have a data to be stored in a memory, then you need to use indirect addressing. You want to clear about 200 locations, one after another, all you need to put 0. You need to have some sort of indirect addressing. Otherwise, it is difficult to do. Otherwise, you're going to go instruction by instruction. So you use indirect addressing. So, for example, clear RAM location from that to that. All of them should be 0. How do you do that? Indirect addressing of data memory is possible by using this particular register, INDF register. As soon as you initiate INDF register, it knows that where to go to find the address. So I want to go to this particular person. I don't have that address, so I do an indirect instruction that tells me where the address is, then I go. That's what it is. So for indirect addressing, you must initiate that particular instruction, INDF. Once you have done that, it will find the address, and I'll show you that in a minute. An instruction of INDF register actually access the 8-bit data file select register. This, as soon as you address this know where to find the address. It goes to FSR, that's where the address is. FSR holds the address, indirect address. And the difference between the indirect and direct addressing, let me explain that to you. So what you do is there are bank 1, bank 2, bank 0, bank 1, bank 2, bank 3. So for direct addressing, what you do is you select RP1 and RP node of your status register. As soon as you put a value 00, it will be this bank. If you put 00, if you put 01 is that bank, and that bank, that bank. That's how you select the addresses. And then, from your opcode, you've got 7 bits here, which will then control all what you need. Okay. Indirect, so what from here you will have the address, and from the address you just read the content. Indirect addressing means what happens is you need to select which register is. You don't use this technique. There is a bit called IRP, which is in the status register. You need to set that value. So I wanted to address this particular bank. This one I want to address. I know it's in bank 2. I know I need to put 10. So I go and put 1 here and 0 there. In my FSR register, the last bit 7, I put 0. And then IRP, I said this is to 1. And indirect addressing using that as the bank selection. And the remaining bits are used as the memory location. And you read the content out. That's how you do. So you may find it difficult, how do we do this? And I'll show you one example. And then you come back again and figure it out once more. So effective 9-bit address is obtained by concatenating the 8-bit FSR register, which is 8-bit FSR register, plus and the IRP is that one. So you'll have effectively 9-bit available, and the 2 bits of this tells you which bank your memory location is going to be, and then this tells you where the memory location is. Okay, let's look at example. This example is very, very simple. Let's see. This program stores the value 0 to 15. So I'm only interested in 16 locations from H20 to 20F. So I know from memory 20, I want to put value 1, next one 2, next one 3, and then when I come to here, I want to put a value 15 into it, one after another. How do I do that? I know it's in bank 0. So in indirect addressing, I have to make sure I've got this is 0, that selects the banks. So bank 0. So I go to my thing and I just say BCF start as 7th bit to 0. So I've selected that as 0. Then I move literal word W register 20. So this is 20. And that's stored in FSR register. FSR register is here where I'm storing 20. Here go. This is 4 bits and that's 20. It's stored. So I'm pointing now that register now. Then we are saying load the W register with 1 because I have got to put 1 here first. So I need to go to that particular register indirectly. So what I do is you say move the W register content to INDF. As soon as you initiate INDF instruction, it automatically knows the addresses in FSR. It will automatically pick it up. As soon as you initiate this one, it will take the W content memory and put it in FSR. FSR is 20 because we loaded 20. So the 20 register will have 1. Now what you do in the W register, you add 1 to it. So increment the W register. Then you say increment FSR. So FSR is incremented. FSR is incremented means pointing that one. And it's pointing that one. And then that's incremented. Now you check whether you have done all the 15. When you finished all the 15, that means that's 15. When you add another 1 to it, this bit will become 1. Because 1, 1, when you add them 0, 0, 0, 0, and a carry bit goes in as 1. So we look for this particular bit. Whenever it's 1, that means you're finished. So that's what this says. I'm checking whether that bit is, 4th bit is, that is 0, 1, 2, 3, 4th bit is set. If it is not set, that means I still have to keep looping and increment. If it is set, I come out. That's all the program is. So when I come out, all these locations would have the value 1 to 15 and these are the locations. This will only work like when you want to do consecutive. You can do other way as well without consecutive, but that's what it is. Normally, if you want to store data in a lookup table, you use this instruction. First, initially put the values in here and use this indirect addressing to locate the position. And you will do an exercise on the next example using this particular indirect addressing. You can now try as a group, write a program to clear the memory location from that to that. I want these to be all zeros. Can you write a program to clear all the memory using indirect addressing? You can do other way as well, but using indirect addressing, can you clear them? That's all the theory for timing and delay loops and indirect addressing. That's all this particular chapter covers. Now you have to do 2 lab activities, and There's no particular time as. Once you have finished the first 4 lab activities, you can start to look at the 5th one. We've got two keys, push button keys, one here and the second one here. And if you press this one, your microcomputer should detect that it's been pressed, and it should increment a counter inside, and that counter contains send here. If this is pressed, then it should decrement the counter that you have, and the content is sent here. So these two, one increment, one decrement. You will notice that here, there is no binary to BCD chip, which was earlier you used them. You don't have that. You need to implement that inside the program. So you need to store all these pattern, A, B, C, D, E, F, this pattern inside. And whenever you have the appropriate counter value, you have a lookup table consisting of all these patterns, all the pattern values. Whenever you have the particular counter value, it points to the right memory location, and that value is sent, and this will then display 5, 6, 7, 2, 3, that, So you need to have a lookup table. So you need to use indirect addressing to create that lookup table, and then take the data from that, send it to the 7-segment display. So I'm trying to avoid the hardware that you used in previous exercise, I think in activity 4, activity 3, and I'm trying to avoid that and use software so that hardware is minimized. That's this example. And the next example is a door open or close detector. If a door is open, it should pulse a light, or it should alarm. So in this case, we are saying if a door is open, you should flash an LED. So the switch is connected to PC node, and close to open condition of the door as shown in the diagram. Okay. So when you close it, LED should be glow. When it's open, it should be off. So the switch's closed position is equal to the door being closed. Write an assembly program which continuously reading PC node and detect if the door is open. When the door remains open, an LED connected to the PCD should flash that every 5 milliseconds, so every 5 seconds. So it should create a pulse like that and should flash at a 0.5 second interval continuously. So you could have a 0.5 second period. You must write the delay route in 0.5 second, assuming a clock frequency of 4 megahertz. You could have it this way, or you could have, duty cycle of, almost 100% as well. I leave it to you to do whichever way you want to do it. But it is 0.5 second. It should roughly, delay must be 0.5 second. And so you turn on for 0.5 second, then immediately turn on. So it's like this way. So turn on 0.5 second, turn off then 0.5, turn on, turn off, 0.5, 0.5, 0.5. You can do that way as well. Again, these are the 3 references I have used, and there are other references also you can look up. There are quite a lot of references available on the web, but I think there are quite a lot there in different ways people have written it, but I've kind of condensed them in a way that you can understand. Once you have understood, once you have done the activity, you will be able to do any other questions without any problem. All right, that finishes this particular chapter.